Welcome, listeners. Again, we'll start our discussion on the second part on the topic of metamorphic rocks. So, we have started our discussion on metamorphic grade, we have seen that metamorphic rocks can be of varying grade, starting from very low grade metamorphism to low grade, medium grade to high grade. One of the most important, I'll say, discovery is the idea of the different index minerals to differentiate between the different grades of metamorphism, and it was done by George Barrow from the Scottish Highland, where he has noted that up to from as he moved from one place to another in the Scottish Highlands, he found that some of the minerals are appearing at a certain distance, and as they are progressing from one part to the other part of the highland, again some other minerals are occurring and some other minerals are vanishing from the system. So what he proposed, that your minerals, certain minerals are very characteristic of certain pressure temperature zones. So that's how he proposed that if I am looking at a very low grade of metamorphism, then certain minerals will appear in that zone. If I go into the medium grade metamorphism, in that case certain mineral might vanish, some other new minerals might again appear in that intermediate zone, and further to a different zone which is giving you some high grade metamorphic rocks. In that case, some other minerals might occur or might appear as new minerals, and the minerals which were occurring in the low grade domain or in the medium grade domain, those minerals are simply vanishing in that region. So based on that, he proposed the idea of index minerals from low grade to high grade of metamorphism, and this is also termed as or referred to as your Barrovian zone after his name. So that is known as the Barrovian zoning of minerals. So the index minerals, to differentiate between these zones, starting with the first one, that is chloride zone, the most characteristic mineral in this zone will be definitely chloride, and based on this name the zone has been marked as your chloride zone, which is having a relatively low temperature, about 300 degrees centigrade of its occurrence. Then as we go beyond this temperature to 400 degree centigrade or so, then a new mineral that is appearing at this stage, which was not present in the previous domain, is your biotite, and obviously it is the most characteristic mineral in that particular domain. So biotite, there might be presence of chlorite or muscovite or quartz or sometimes albite as well in that particular zone, but this particular zone marks the first appearance, or this particular boundary between, in a series of metamorphic rocks, this particular boundary marks the first appearance of biotite. Similarly, the first appearance of garnet marks the garnet zone. The first appearance of staurolite, kyanite and sillimanite, this also marks the different garnet, kyanite and sillimanite zones. So now if I look at this graph as well, then I can see that based on this, if I look at the chloride zone, then you have muscovite, biotite zone, garnet, staurolite, kyanite and sillimanite zone. You can see there is an increase in the temperature from your chloride zone to the sillimanite zone. Also there is a stability, that how far the first occurrence of the mineral is starting from which temperature, and how far it is being able to sustain itself, or that mineral is stable till how much temperature. So you can have an idea just by looking at this graph that chlorite has a stability of around 500, or you can say 520-30 degrees centigrade maximum. Beyond that, there will be no occurrence or no presence of chlorite in the metamorphic rocks. Similarly, muscovite has a much larger stability zone, you can say, starting from about 350 degrees centigrade, it is going beyond 600 degrees centigrade. Then your biotite zone, which marks the first occurrence of biotite, it is between 400 to about 650 degrees centigrade again. Then you have the garnet zone, which will appear at 500 degrees centigrade and will go beyond 700 degrees centigrade. You also have staurolite, kyanite and sillimanite zones, which marks again the first occurrence of or the first appearance of that particular mineral. But in case of staurolite, kyanite and sillimanite, the stability range is a little bit constrained. They are a little less than that of the other mica minerals like biotite, chlorite or muscovite. So in high temperature condition, you will get this staurolite, kyanite and sillimanite mineral. In the low grade, you get chlorite followed by muscovite, biotite. In between, you have garnet and staurolite as well. So this sequence of zones, or that marks again the first appearance or the first occurrence of a mineral, which will be now termed as an index mineral, will mark also the different zones of metamorphism in a regional metamorphic province. Then also, apart from this, as this occurrence or appearance of the first appearance of a particular mineral, it also reflects certain temperature, because for example, if I take muscovite, then it is first occurring at about 350 degree centigrade, then it is present till 600 degree centigrade or beyond 600 degree centigrade as well. So in that case, what is happening, that you can say that it also, not only it is occurrence of the first or appearance or the first appearance of a mineral, it is also giving you an indication of the changes in the temperature gradient. So there you can also say that this zone boundaries are also expressed in terms of isograd. These isograd are nothing but the zones, or you can say lines of same temperature. So here in this graph again I can say, so if this is your garnet zone, then here your garnet will occur first, and this will also reflect a temperature of about 500 degrees centigrade. So this is how your metamorphic zones are divided in a regional metamorphic province. Then there is a different geologist who came up with the idea of your metamorphic facies, and it was proposed by Escola. So he proposed that though the idea of metamorphic grade is fine, but it is not only that a single mineral is present or a single mineral is stable in a particular pressure temperature range. So he proposed that actually there are a series of minerals, or you can say assemblage of minerals, that are present in a particular pressure temperature regime. So he proposed the idea of a facies also based on the or you can say the taken into consideration the bulk composition of an area, because that will reflect that which kind of mineral or which kind of metamorphic mineral will form when it is subject to a specific pressure temperature regime. So the concept of metamorphic zoning and index mineral hold good if only if the bulk composition in an area remains same. But if the bulk composition in an area is also changing, that you have various igneous and sedimentary rocks that are present side by side, and they are completely as a whole they are going under metamorphism, then obviously there is some changes in the bulk composition. So that will now be treated as under the presence of a specific group of minerals, or what we can say assemblage of minerals under a specific pressure temperature regime. So based on this idea, Escola suggested the scheme of metamorphic facies, which defined the broader pressure temperature condition under which a few mineral or assemblage of minerals are stable. So a metamorphic facies is set of metamorphic mineral assemblages repeatedly associated in space and time. So there is a constant and therefore predictable relation between mineral composition and the bulk rock composition. So in summary, between your metamorphic grade and facies, we can say the rocks of identical bulk composition and identical mineral assemblage must have been metamorphosed in identical PT conditions and then they will belong surely to a specific metamorphic facies. So in comparison to grade, where we were only considering the first appearance or disappearance of some mineral along with its formation temperature or temperature of its first occurrence and disappearance of that mineral at certain other temperature. In case of metamorphic facies, this is much of an holistic approach, that here you are not only relying on a specific index mineral, you are considering an assemblage of mineral, and again it is also referring to the composition of the protoliths. It is also giving you a range of pressure temperature condition within which this assemblage of minerals are occurring, or this assemblage of minerals are stable in that particular pressure temperature regime. It is not as that a specific temperature, it is always a range of temperature, it is always a range of pressure. We will see some diagram on that. Then rocks of a specific bulk composition metamorphosed under different facies condition will produce different mineral assemblies. So here it is again a very important point. Though the bulk composition of a specific mineral, the bulk composition of a specific rock in a region could be same, but if it is subjected to different pressure temperature condition, if it is subjected to a very you can say low temperature pressure regime belonging to low metamorphic grade, and again it is getting subjected at a different time to higher grade of metamorphism, in that case what will happen, that it will give you obviously a new mineral assemblage, and that will be not identical to one another. So again the rocks of a specific bulk composition metamorphosed under different facies condition, again that facies condition represents your pressure temperature regime, will produce different mineral assemblages. So different minerals will form subjected to different pressure temperature condition, though the initial bulk composition was same. The third important point is that rocks metamorphosed in same facies condition but showing different mineral assemblages must have different bulk composition. So now if the rocks or the if you are in a specific, now in a different way, on the other way, if you are concentrating on a specific facies, so it will have its limits of pressure temperature conditions, but it is showing or different mineral assemblages you are getting, that will definitely reflect that if this is the facies condition, this is my range of pressure temperature condition, but I am getting two different assemblages at two different time, then I will definitely say that there must be a variation in the bulk composition between in the two results. That means there has to be some different protolith, or the composition of the protolith has also varied from place to place, or some different two rocks. For example, sandstone has been subjected to metamorphism, shale has been subjected to metamorphism in the same pressure temperature condition, but they will eventually give you two mineral assemblage belonging to the bulk composition of sandstone, again a different mineral assemblage belonging to the bulk composition of shale. So this is the idea of facies, which is nowadays a more acceptable one, though there is no question that the initial idea of metamorphic grade also holds good. So a few characteristics, if I look at the metamorphic facies, then each facies is defined by a set of mineral assemblages developed in metamorphic rocks or metapelatic rocks, and are characteristically different from Barrovian zones which only use index minerals. So here again you are taking mineral assemblage, you are not relying on a single mineral only. It identifies the regularities and consistencies in mineral composition and bulk rock chemistry as a function of pressure and temperature. Boundaries between the different facies coincide with different mineral reactions encountered in metapelatic or metamorphic rocks at certain pressure temperature condition. This temperature dependent reaction with very high enthalpy are mostly devolatilization in nature, and hence their positions in PT space are very much dependent upon the composition and quantity of the fluid that is already present. And this the boundaries between two consecutive phases, we will look at a chart of phases. Two consecutive phases are not a fixed line, rather a zone in pressure temperature space. So there are total 11 different established phases, and there are 7 that are characteristic of your regional metamorphic condition. There are 4 phases that are characteristic of your contact metamorphism or contact metamorphic zones. So for regional, you have zeolite, prehnite, pumpelite, green schist, amphibolite, granulite, blue schist, eclogite phases. For contact metamorphic rocks, you have your alabite, epidote, hornfelsic phases, hornblende, hornfelsic phases, pyroxene, hornfelsic phases, and sanidine phases. So if I again look at this diagram now, again looking at a zone of subduction, you can see a subducting plate that is going bowing down beneath an overriding slab here, or overriding plate here. Then here at low depth, you can say, where your pressure temperature is also low, you will get your green schist phases metamorphism. Here you will get at higher or elevated pressure temperature condition, you will get amphibolite phases. At further higher temperature and pressure and very high temperature in the contact with the zone of melting, you will get granulite phases. At very high pressure and temperature in the subducting slab, you will get eclogite phases. Also in between green schist and eclogite, you will have the zone of blue schist phases, which is also a very characteristic feature of your paired metamorphic belt. We will have a small discussion on that as well later on. So this is a chart or figure, pressure versus temperature diagram, where you can see the zones, or I'll say the phases of different assemblages. So here you have the zeolite phases, then prehnite, pumpelite, then you have green schist, amphibolite, granulite, blue schist, eclogite. So these are all your phases that are related with your regional metamorphism, but there are also these 4 phases, your this one, alabite, epidote, hornflens, then hornblende, hornflens, then your pyroxene hornfels, and you have sanidinite phases as well. These are mainly temperature dependent, that's why there is not much pressure that is involved in this kind of phases. Here you will get mainly temperature driven metamorphism, that is again a characteristic phenomenon of your contact metamorphism. So here that's why these phases have been kept very near to the temperature arm. You can say there is only change in the temperature, not much change in the pressure. But from zeolite to blue schist, you can say there is high change in pressure condition. Eclogite is the most both high temperature pressure condition. Granulite is very high temperature and also relatively high pressure condition. Green schist is relatively low both temperature and pressure condition. Intermediate, you have this amphibolite phases as well. So there will be certain mineral assemblage, they will be characteristic to this individual phases. Now if I go one by one, then the first phases of regional metamorphism, that is zeolite, you have this lowest pressure temperature condition of metamorphism. The temperature might range between 150 to 300 degrees centigrade, and the pressure will be about your 3 to 4 kilobar maximum. In that case, the main characteristic minerals or the assemblies that you will get is your zeolite, quartz, alabite, and clay minerals. Talking about prehnite, pumpelite phases, it is mainly encountered in basic or metabasic rock subjected to your burial metamorphism. Here the mineral assemblage is characterized by prehnite, pumpelite, chlorite, calcite, and zeolite. Sometimes zeolite is present, sometimes it is absent. Then you have the other type of regional metamorphic phases, that is green schist phases, and it is a transition from prehnite to green schist, and it is marked by the breakdown of prehnite and zeolite at around 400 degrees centigrade. So if the protolith is metabasic in nature or basic rock like we discussed in igneous, so if that the protolith of this metamorphic rock is a basic rock which have very low amount of silica in it, in that case your mineral assemblage will be mainly chlorite, albite, zoisite, quartz, actinolite, epidote, sometimes calcite, sphene or ilmenite might be also present. If the protolith is metapelitic in nature now, in that case you have the mineral assemblage of chlorite, muscovite, biotite, sometimes albite or chloritoid or alumina silicate are also present. If again the protolith is of meta-Grey-Wacke nature, in that case you will get albite, epidote, muscovite, chlorite, quartz, sometimes biotite. If it is a calsilicate rock, if the protolith is, for example, you are looking at a protolith that is calcium carbonate, that is limestone, that is going into transition to marble. So if that is the metamorphic rock or the calcilicate metamorphic rock, which protolith was a limestone, in that case the characteristic mineral assemblage you will get obviously dolomite, calcite, quartz, talc, sometimes tremolite as well. So these are the different, you can say, mineral assemblage that will define this each and every facies, as well as just by looking at the mineral assemblage you can also have an idea about the protolith like we just did. For example, for metabasic metamorphic rocks, the protolith has to be a basic rock. Okay, for meta-Grey-Wacke the protolith has to be a Grey-Wacke, which is also a kind of sandstone, but it is having less amount of quartz grains in it, like we discussed in the classification of your sedimentary rocks. And for calcilicate rocks which have a protolith of limestone prior to the metamorphism. So these are the different metamorphic mineral assemblages. Green schist amphibolite transition zone, in case of metabasic rocks you will have transition from albite to oligoclase. Amphiboles will become more aluminum rich, chlorite will become more magnesium rich, epidote will decrease and eventually disappears, and the characteristic again mineral assemblage will be epidote, then hornblende, then oligoclase and chlorite. In pelitic rocks the mineral assemblage, obviously garnet will occur at this moment of green schist and amphibolite facies transition zone. Garnet will occur here for the first time in terms of facies, not in terms of grade we are referring here, we are talking about facies now. So garnet makes its first appearance at this transition. In case of again when the protolith is a limestone, the calcilicate will have characteristic assemblage of dolomite, tremolite, quartz, sometimes talc and calcite as well. Then you have amphibolite facies which has a temperature regime of near about 550 degrees centigrade. Again, if the protolith is a basic rock, you will have an assemblage of hornblende, andesine, which is again, andesine is again a plagioclase feldspar. Plus minus garnet or epidote might be also present. In case of pelitic protolith, in that case the metamorphic rock will bear these minerals: staurolite, garnet, muscovite, biotite, kyanite, sometimes sillimanite, quartz, and again a plagioclase feldspar, that is albite. In case when the protolith is a limestone, in case of calcilicate rocks, you will have an assemblage of dolomite, diopside, quartz, plus minus sometimes an olivine, that is phosphorite, and a specific type of garnet. Then again from amphibolite to granulite transition, you have this clinopyroxene will get stabilized here. In case where your protolith is a basic rock, again the main assemblage of the mineral will be hornblende, plagioclase, sometimes plus minus titanite and sphene as well. In case of, on the other hand, in case of the pelitic protolith, you will have muscovite, quartz, plus minus albite. Sometimes they react and form potassium feldspar, sillimanite, and the water will be simply thrown out of the system. For granulite facies, which is definitely very high temperature and relatively high pressure as well. In that case, in case of basic protolith, you have a metamorphic rock, new metabasic metamorphic rock with assemblage of orthopyroxene, clinopyroxene, plagioclase, sometimes associated with hornblende, garnet, biotite, quartz, rutile and ilmenite. In case again the protolith is pelitic in nature, in that case you will definitely get perthitic. K feldspar, perthite is a kind of a texture, but you can simply remember K feldspar. Plus sillimanite, garnet, hypersthene, albite, hercynite and quartz as well. In case when the protolith is a limestone and the rock will be a calcilicate metamorphic rock, you will get some carbonate minerals, scapolite, olastonite, some garnet, plagioclase, fene and sometimes quartz and calcite as well. Then you have the blue schist one. It is only if possible to get blue schist facies in paired metamorphic belt where you have high pressure and low temperature facies of regional metamorphism, like we have seen in the subduction zone, where the pressure on the downgoing slab is very high but the temperature is relatively low. In that case, you will get a very characteristic mineral assemblage, that is glaucophene, lozonite, albite, chlorite and aragonite. And the transition between the green schist and blue schist will also give you glaucophene, epidote, albite, actinolite. Now the eclogite one, which is possibly the most high temperature, high pressure condition, there you will get a characteristic garnet, that is pyrope. It's a type of garnet, so it's pyrope garnet, and a very characteristic pyroxene, that is also a very specific kind of pyroxene, that is omphacetic pyroxene. In case where again your protolith is your metasediment sediments that are now transformed into metasediments, so you will get in eclogite talc, kyanite and phengitic muscovite as well, which is also termed as white schist. Then in high pressure, moderate temperature eclogite facies, you will get amphibole and garnet, and it also getting transition from example blue schist to eclogite facies. In transition zone between granulite and eclogite, means only in the higher temperature side of the diagram I was referring to, you will only get omphacetic pyroxene and pyrope garnet. And for your contact metamorphic facies, you will get sanidinite facies, which is the highest temperature facies in a contact metamorphic zone. There, if the protolith again is a basic rock, you will get plagioclase, hypersthene, augite and tridymite. But in case of a pelitic protolith, you will get sanidine, cordierite, spinel, hypersthene and sillimanite. So you can see that these mineral assemblages are obviously again and again, these mineral assemblages, now again coming back to the same diagram, but now the mineral assemblages are also mentioned here. So you can see some of the mineral assemblages or the stability of the minerals reflect that in which facies this mineral will be more stable, in which facies there will be no occurrence of a particular minerals, or in a facies where there will be some new occurrence of a new mineral. So this facies diagram again, to summarize, will give you an idea that if this is the pressure temperature domain of a particular facies, then this facies will give you a specific set of mineral assemblages. If there is some changes in the mineral assemblages in the same facies, then it is nothing but a function of its original composition of the protolith. So if the composition of the protolith is same, then in a particular facies you will get same mineral assemblage. But if the protolith is also changing, the composition of the protolith is not same, but it is subjected to a specific temperature pressure regime, it might give you other mineral assemblages in the same metamorphic facies. So before I conclude the second part on our discussion on metamorphism, here are some diagrams, or you can say photographs of some zeolite, this one prehnite, pumpelite, some amphibolite facies rock, blue schist facies rock, green schist facies rock here, and also the most highest pressure temperature metamorphic condition, that is your eclogite facies. So here I will stop our discussion on metamorphic facies. We'll come back with metamorphic texture in our next lecture, but just to give you an idea, very quickly we'll be again discussing in detail about this. So I can look at this samples. These are obviously metamorphic rock. So if again I am taking a shell that is subjected to your metamorphism, then that shell will first get transformed into a rock like this. Obviously this is slate. So this is, you can say, very low grade metamorphism of shell that is giving you a rock that is slate. So if I increase the grade, then the same slate will get transformed into a rock that is phyllite, which will also have some planar features. In both the cases you can say that there are planar features which are present within the rock. Further, if I increase the grade further, then again I will increase the grade like this. This will become a schist. So now the same shell which was actually sedimentary in nature is now becoming slate at low grade, at very low grade, then low grade it is your phyllite, then followed by the presence of schist at the moderate grade. Relatively high grade, what you will get this kind of bandings which are referred to as gneisses. So now if I simply look at the original scenario will be like this, that will start with a shell that is being subjected to burial under the earth. That shell will get transformed into shell first, then the same slate first, then that same shell will get transformed into phyllite. As I increase the metamorphic grade, again the same shell will get transformed into schist like this one, and then the same rock will be finally transformed into a gneiss like this, with very beautiful bandings of light and dark colored minerals. So we will be discussing with these structures and texture in metamorphic rock in our next lecture. Thank you.